previous time we were discussing the tangent spaces of products. So we came to the point where we were able to identify the tangent space of the product manifold with the direct sum of tangent spaces of individual manifolds. Okay, so today we're gonna do like some sort of two short exercises regarding this. So second exercise here would be, so the Roman I was already solved, right? This is just the what we did above. So the second exercise is to determine how V comma W from T PM O plus TQN acts on F from C infinity M times N. So this means a smooth function on the product, right? Well, this is now really simple. We have V comma W on F. So by 1, what we get is, so now we use, where is it? We use the formula that is given by this isomorphism, right? Isomorphism between the tangent space of the product manifold versus the direct sum of tangent spaces. Okay, so what we get here is f of v of f of inclusion. So now this is the inclusion of M at Q, right? And the second summand is W on F of inclusion and P. Okay. So now what this is really is, this just means that we are evaluating our derivation V on this function here. So we are holding Q still and like only taking the function with regards to its first argument and then evaluating V on this function, right? And the second one is then f of p comma dot. Okay. So now, furthermore, what we have is, so this is the end of this exercise, right? How this couple VW acts on F. Like for the last part of this exercise, let G be a smooth map between manifolds. This is in the abstract sense, right? So Q is also a smooth manifold. So now what we have to do is calculate dg at point PQ of VQ. So we want to know how the differential of a smooth map acts, oh sorry, VW is this, right? How the differential of a smooth map acts on like this couple v comma w from the direct sum of tangent spaces. Okay, so what we have to do is we check what this thing does on some f that is now a function on q, right? Okay, and this is nothing else but v comma w of f of g, right? But this is now by second part is this v on f of g of inclusion of m at point q plus w of f of g of inclusion n into the product at point p. Okay, but this now by using the definition of what the differential is, right? The differential map. I see some things in the chat. Okay, I hope that you can all hear me. So yeah, now what we do is we use the definition of the differential of this map, g of inclusion mq, right? And what we get is d of g of inclusion mq at point P evaluated on V and then on F, right? So this is just by definition of this D here. And the second part similarly, right? Okay. So this now implies, since this holds for any f, right, for any smooth function on q, this implies that dg p comma q on v comma w is equal to like just this first part. Right, we just omit this f that's here. Okay, so this is now kind of important, right, when dealing with any kinds of actions, you know, like say that a group acts smoothly on your manifold, right? You may want to sometimes differentiate this action, and this formula will precisely be of use when doing that, right? So, and for the fourth part of this exercise, and this is homework now, calculate the velocity of the following curve. So this is now a curve that starts at point P in M, and this or a path would be more precise, right? A path that starts in Q in N. Okay, and G is again something smooth from M times N to Q. So, and you should calculate this. Right, you may want to try using like the above steps and maybe the third part of this exercise. But we're not going to do it here. We're going to move on to what's planned for today. Have you all, I'm sorry, was I too fast? Did you all write down what's written here? Did you manage?
Maybe just 10 seconds.
Okay, I can wait.
Okay.
Good. Well, for today, like the main part of today's exercise sessions, we're going to discuss immersions, submersions, embeddings. Okay, so first of all, let's state some definitions, right? Before we even begin, let G from M into N be a smooth map between smooth manifolds. Okay, whenever I say smooth map, I mean smooth in the abstract sense between two smooth manifolds. Okay, this should now be clear. So let's state some definitions here. So G is said to be an immersion at point X if what holds?
The derivative is injective.
Yes. dgx injective. So this is, of course, a map that goes from txm into tg of x n, right? And it's a linear map, and we may always discuss whether this map is injective or whatever, right? So a submersion, can you shoot out the answer?
If it's surjective?
Yes. Okay, so the next thing would be a local diffeomorphism, right? So again, at X. Can anybody tell me?
If it's diffeomorphic on some neighborhood of X.
Yes, something like that. So if there exists, so how should I write this? I'm just gonna write it like so. There exists an open, open neighborhood U of X, and V an open neighborhood of G of X such that the restriction of G to U, and this now goes from U to V, should go from U to V, is a diffeomorphism. Okay. That's what it means to be a local diffeomorphism. So then we also define what it means to be an embedding. So what does it mean to be an embedding?
If it's all three at once.
Sorry?
If it's all three at once.
No.
No, the function has to be injective, not the derivative.
Okay, well, kind of the derivative also has to be injective here. But now at every point.
Image of X must be a submanifold
It's image
of the first manifold. So in our case, M
okay.
must be a submanifold on N.
Okay, yeah, well, that's at least how we try to envision everything, but in the abstract sense, this is not the definition. It's more or less, how should I say, a consequence. What you said holds indeed for the image of our map, but it's more of a consequence of this definition. So two things. Okay, first of all, of course it's smooth, right? G is smooth, but now so first of all, it has to be an immersion, okay? So it has to somehow not squeeze any parts of the tangent space, like for it to have a lesser dimension in its image, right? That's the first condition on what it means to be an embedding. So, but immersion at all points, right? We just omit at X because we just say it's an immersion, okay? But that's not all. Does anybody know what else has to hold for this G?
Homomorphism on its image in topological sense.
Yes. So, topological embedding, right? So this means i.e. G M into G of M is a homeomorphism. Okay. So this means that if we restrict the codomain only to its image, well, then it has to be bijective. So this immediately implies that G has to be injective. Okay, that there's no other way for this to hold. And now not only that, but with respect to subspace topology, we have to map open sets to open sets, and the pre-images of open sets, of course, must be open in order for this map to be continuous. So that's altogether means that the restriction of this map onto its image is a homeomorphism, right? The restriction of the codomain, not the domain. Okay, and we also define what a rank is. So this now, yeah, it doesn't continue this sentence here. Okay, I'm just gonna write it here nevertheless. Rank x of G is defined as the dimension of the image of dgx. So this is like some point in M now, right? Of course, this rank is not necessarily everywhere the same, right? So can you think of any easy examples for an immersion and a submersion?
A submersion would be a projection.
Yeah, of Euclidean spaces, right? So this is a projection, and here n must be greater or equal to m. How about an immersion?
Inclusion.
Yes. Well, these two examples are easy, and we're gonna state a theorem now, which says that locally every map looks like a projection or an inclusion. Okay, so this is a really important theorem. And it's called rank theorem. Okay, so this holds what I just said, that every map looks locally like a projection or inclusion, if and only if it has constant rank. Okay, so if G from C infinity M comma N has constant rank R, so this X is here now arbitrary, right? Then for any X in M, there exist, chart neighborhoods U phi in M of X and V theta in M of G of X such that G of U is under V, and drum roll, we have the following beautiful equality. So this is now precisely what we've stated above. So x1 comma dots comma xm x1 dots xn minus oops, this is just r xr, and here we have zeros in the end. Okay, so this is n minus r zeros. And this is precisely what we've said before, right? Either it's a projection or it's an inclusion. In the case where for example, if we're dealing with a submersion, here we would have R equal to n, so there would not be any zeros left, right? Okay, so necessarily m would be greater than R in the case of a submersion. But in the case of an immersion, R would be equal to m. Okay, so the dimension of the domain, right? So, and there would be n minus m zeros in the end, which immediately means that the dimension of the codomain must be greater than the dimension of the domain. Okay, so yeah, I'm not going to write this down. This is like something that just ask yourself, what happens if my G is a submersion, or if my G is an immersion, and you'll get to the same conclusion as I just did. Okay. So, okay, we have the following corollaries, following important corollaries. So first, inverse map theorem on manifolds. Okay, it says that if dgx that goes from txm into tg of x m, if this map is an isomorphism of vector spaces, right? Then G is what? Can you finish my sentence?
Invertible.
No.
Diffeomorphism. Local.
Yes, so it is invertible, but only locally. Okay, so this is a local statement. G is a local diffeomorphism. Okay, this now would follow because if it's an isomorphism at one point, it must necessarily be like this dgx must necessarily be an isomorphism like on some neighborhood of x. Okay, so this matrix must necessarily be invertible around this x. Okay, so on some neighborhood, and on this neighborhood we use rank theorem, and what we get is just that this whole composition that we've written above is an identity map. So locally it looks like an identity map. That's all it says. Okay, and the second corollary that's maybe even more important at times is implicit map theorem on manifolds. And it says that if Q from M is a regular value of G, so G is again assumed to be a smooth function between M and N. What this means is G is a submersion at points at all points, right, in G pre-image Q. Then, can you finish my sentence? then this G minus 1Q is
A submanifold?
yes. Of what kind?
Smooth?
Okay. Anything more?
Closed.
Okay. Automatically, since the pre-image of singleton, right? Yeah, well, embedded is the right adjective, right? We have two kinds of manifolds. One are immersed and the others are embedded. And its dimension is this. This means that its codimension is n, right? Codimension n. So yeah, sometimes we write this as okay. So let's begin solving exercises. First exercise would be let Q from n be a regular value of a smooth map G that goes from M into N, right? Determine the tangent space Tx of the manifold G inverse of Q. So the tangent space of the submanifold that we get from the implicit map theorem. Okay. For all x, of course, from this manifold. Any ideas?
Maybe we can take just the tangent space of the on the n manifold and then map it with the inverse of the tangent with the inverse of dg.
Okay, so dg is surjective. It's not necessarily injective. So we do not necessarily have an inverse. Actually, there's no reason to believe that we do. Okay, but think in terms of dimensions. What is the dimension of this space?
One less than codimension of n.
Why one less?
Because I thought that tangent space is less. Yeah, never mind.
Yeah, well, it's not one less. It's precisely the dimension of the manifold G pre-image at point Q. Okay, but as we've stated above, this is nothing else but dim m minus dim n. Okay? Now we utilize a linear algebraic fact. Rank nullity theorem. This is really important from linear algebra. And what does it say? It says that, so look, dgx is a map that goes from txm into tg of xn, okay? So it says that the dimension of the domain of this map is equal to the dimension of the kernel of this map plus the dimension of the image of this map. Okay? But now we just read everything off. This is nothing else but the dimension of M. And this is nothing else but dimension of N, right? Since dgx is a submersion, right? At point X, since like X is a regular point, right? Okay, so what we get is that the dimension of kernel of dgx is equal to dim m minus dim n. Okay, so now we take a look at these dimensions and we see that they're the same. So what we do is we try to prove that tx g minus 1 q is the same as kernel dgx. So how do we go around proving this? I'm just gonna ask you straightforwardly, why is it enough to prove only one inclusion?
Because they're finite dimensional vector spaces.
Of the same dimension. We just proved that they're the same dimension, right? So enough to prove only one direction. So this, look, this rank nullity, extremely important, okay? If I can make a square around it and go take a look how it's proved and stuff. This is really important. So it's enough only to prove one direction. And of course, we're going to try to prove the inclusion from left to right, because we're just going to try to like take a v from tx g minus 1 q, and we're going to evaluate dgx on this v. Okay, but what we have to do is, of course, we have to somehow take this map for a walk. Okay, this is now a smooth function on n. Okay, by definition of this small d here, we have v of f of g, right? But now what? F of g. What does it do? This is a smooth map. From M into R. But this now here, V, is a derivation on the manifold G minus 1 of Q. Okay, so actually, this isn't M here. This here is G minus 1 of Q. Okay, so cross this out, G minus 1 of Q. Can anybody tell me what I'm going to write here? What can be said about this map, f of G? Is the question too simple?
No, I don't know what can be said. Is the reason why I'm not answering.
What does G do on G to the power of minus 1 of Q?
It maps it into Q.
It maps everything into Q. So f of G is what?
F of Q.
F of Q, constant. Okay? This is constant f of Q. Right? What do derivations do on constant functions?
Map them to 0.
Exactly. So this is it. We've proven it. Right? We've proven the desired inclusion. Okay, so this is really important, since now any kind of space that you give me, maybe not any kind of space, for example, a sphere or something like that. Okay, I may write down the sphere using the implicit map theorem and then easily conceive what its tangent space at any point is, because I just look at the kernel of this of this differential of my function at that point. Okay, so that's really useful. You're going to be using this all the time. Okay, let's move on. So which one are we gonna do for the end of this hour? Let G go from R into S1, be given by G of X is equal to e to the power of 2 pi I X. Prove that G is a local diffel. How do we do this?
We take a neighborhood of any x under real numbers and prove that the function on that neighborhood is a diffeomorphism.
Yeah, okay, that's a straightforward way of showing it. I have a better way. Don't we have a theorem written above? Like, I think it's written here, right?
The inverse map theorem.
Yeah, exactly. So we're going to use the inverse map theorem in order to conclude this, that it's a local diffeomorphism, right? So first of all, let's draw a sketch that everyone always draws when considering this map. This is essentially what we're doing, okay? This is R, and here we have a G and S1. Okay, so that's how it should be envisioned. You are kind of twisting this R onto your S1 or something like that. Okay, so now we're gonna take a look at the map dgx that goes from txr into t e to the power of 2 pi I x s1. Okay, let's finish this and then we'll have a break. This is a short exercise, so it shouldn't be too long. What is txr?
R?
Yeah, it can be identified with R because R is a vector space. Any, like, the tangent point, the tangent space of a vector space is of course the space itself, right? So, I mean, this is an identification that you do in your head. Okay, you have to interpret it correctly. So that's what we're going to try and do. Well, how about this one?
Yeah, this one isn't an identity of S1.
Sorry?
This one isn't S1, if I recall correctly.
No, of course it can't be, because S1 is not a vector space. It's a manifold. S1 is a manifold, a smooth one. So of course, what we are trying to do is, this is S1, right? And you are given a point here, and now you want to kind of try and describe what this here is. Okay. So if you don't have any idea how to do this, you write down S1 and you say, okay, this is everything from the complex plane that has the absolute value equal to 1. Okay. So you may write S1 is the pre-image via phi, where phi is now nothing else but something that goes from C into R. Okay, so this is essentially the same as R squared, and now this phi is nothing else but x plus iy is equal to x squared plus y squared, right? So so now we are trying to somehow utilize this implicit map theorem to describe S1, like just as we go or something, okay? So what we do is we take a look at its differential at point Z, okay? So this may as well be written as x comma y or x plus iy or something like that, okay? And of course, this is nothing else but partial derivatives of this. So the gradient, right? The gradient of this function, x squared plus y squared. So what we get is 2x and 2y. Okay. And like at points from S1, this is a non-zero map. Okay, hence S1 is a smooth manifold. Okay, and now what we have to do, of course, we've already proven that S1 is a smooth manifold. That's why we're going here so fast, because this is really kind of boring in a way. Okay, so this is obviously surjective, since a non-trivial linear map into one-dimensional vector space. Okay, every non-trivial map into a one-dimensional vector space is surjective, okay, by linearity. So to determine the tangent space of S1, what we have to do is we have to take a look at the kernel of d phi z. Okay, so this is now the kernel of the above map, but this is nothing else than the linear span of the vector minus y x, for example. Okay, if I multiply these two vectors that I've written here, I get a 0. Okay, so everything that's inside this kernel is nothing else but the linear span of this vector. Okay, here's where the linear algebra starts kind of happening, because you kind of need to be at home with this. If you're not at home with linear algebra, then you're gonna want to, I don't know, try and have a couple of exercises regarding this. So, but this here now is nothing else than iz, right? Okay, z is x plus iy. So if I multiply this with I get a minus y as the real part, and I get x as the imaginary part. Okay, so one may as well write this as r times iz, and this is perfectly good now, because why? This z here is maybe interpreted as this vector here, right? And iz, what it does is it rotates everything for 90 degrees, right? So what we get is this iz as a vector in two-dimensional Euclidean space, and not only the vector, but the whole line. That's why I'm writing r times iz. Okay, so this is only to interpret what the tangent space of S1 is. Well, what about now? Yeah, well, we have to show that this dgx is a local diffeomorphism, right? We do that by showing that, I mean, dgx must be an isomorphism, okay? But since the codomain, again, is a one-dimensional vector space, we only have to check that dgx is surjective, okay, so that it's non-zero. Okay, so we calculate what dgx of v is, and this is now, of course, you have to take the derivative of your map e to the power of 2 pi I x with respect to x. So what you get is 2 pi I e to the power of 2 pi I x times v. Okay? So what we're doing essentially, what is this v? You're probably asking me now, how do we interpret it? Well, you have like a real line here, okay? You also have like a circle here, and say that you pick a point x here. Well, v is then nothing else but this vector that is attached to your point x. Okay, so this is essentially a number, since our space is one-dimensional. Okay, so this x is now gonna map to, I don't know, here somewhere or something, and the tangent space at this point is this thing. So what this map does is it kind of sends it somewhere onto this tangent space. Okay, it just kind of stretches it. So what we see is that dgx is given by multiplication by 2 pi I e to the power of 2 pi I x. Since this map is non-trivial, between one-dimensional vector spaces, it's an isomorphism. So now everything else is done by using inverse map theorem. So G is a local diffel. Okay. So that's a whole lot of writing for, I don't know, for just an elegant interpretation of what's going on, essentially. We didn't compute much things here, right? We just interpreted the circle in the context of implicit map theorem, and all of these concepts here now, the derivatives and so on, are interpreted in our in like this example of a circle. Okay, do you have any questions?
Jaz bi imel enega, če lahko.
Ja, izvolim.
Tam, ko smo mi hoteli pokazati, da je tangentni prostor enako jedru tistega odvoda.
Ja.
Ok, to razumem, moramo pokazati, da odvod v slika v nič. Samo kaj mene zanima, kaj točen je ta f kle?
Poljubna funkcija na n-ju.
Pol iz n v n.
Ne, iz n v r. Funkcije,
Ok.
funkcije grejo vedno v r, ne? Ali pa v c, no. Se pravi, ja, kot funkcije vedno smatraš realne funkcije oziroma kompleksne funkcije. Pač odvisno, ja, tle se vedno bolj ukvarjamo z realnimi mnogoterostmi in posledično imamo v mislih realne funkcije.
Pol tam naprej, ko smo pa rekli, da f kompozitum g slika, ne, pač slika iz m v r, ja, ok, zato ker itak g slika iz m v n.
Ja.
Samo pa smo pa rekli, da to ni akijeno, g minus n od q. To,
Ja.
ko smo m prečrtali, ker smo rekli, ok, namesto m je dejansko g minus n od q.
Ja.
A to zato, ker je bil ta naš v odvod na točki od g minus n
Ja,
od q.
exactly, ja, točno tako.
Ha, ok, hvala.
Okay, dajmo imeti 5-minutno pauzo. So let's have a 5-minute break and let's continue at 20 past 11. If it's okay with you, I'd like to continue. Let's write down an easy exercise that you will have to solve for your homework. So an exercise. The lemniscate is the image of the map. So phi goes from minus pi to pi into r squared, and it's given by phi of t is equal to sine 2t on the first argument and sine t on the second argument. So prove that phi is an injective immersion that isn't an embedding. So let's just sketch what this thing here is. It's kind of a figure 8, something like this. I draw it really poorly. I'm going to try and draw this a bit more aesthetically pleasingly. So I guess something like this. So what happens here is that we have like sort of, you know, arrows here, but this point here, it isn't excluded because it's this 0 point isn't excluded because at t equals to 0, we are mapping everything to 0. Okay, so indeed it is a figure 8 curve. Okay, it's not missing any point. Yeah, so for the part where this where you have to prove that this isn't an embedding, just take a look at the compactness of this thing and the compactness of your domain. Okay, so everything else is pretty straightforward. All right. Let's go and start discussing some important Lie groups. Okay. So we've already met the Lie group GL and F, right? Now we're going to meet the special linear n times group of n times n matrices. So these are all matrices in GL and F such that the determinant of any matrix inside it is equal to 1. Okay. Prove that this is a smooth embedded submanifold of GL and F. So what's our weapon of choice?
Da pokažemo da je regular value.
Yeah, we're gonna use the implicit map theorem for manifolds, right? That's it's kind of our only hope for doing this. So solution. Of course, we have the determinant map, right? That goes from not only it goes from GL, it goes from F n times n, and it maps to F, right? This is the determinant map, but okay, we may restrict it to the map. I'm not going to write any kinds of indexes or restriction signs here. I'm just going to write GL and F. I mean, I'm going to use the same, like, I'm going to write that for this, this map as well. So this is F without 0, which is F star. Okay, this is how we denote the F without 0. F here is field, obviously, right? This is either real or complex numbers. Okay, so in order to utilize the implicit map theorem, we have to show that 1 is a regular value of that. Now that is, of course, a smooth map, right? It's just a polynomial in n times n variables. So what we have to do is determine its derivative, right? This is what we want to show, that it is surjective. Okay, so first off, we calculate d of that at point I. So at the identity matrix, which is of course in special linear group, right? Okay. And this is a map that goes from what? T, I, G, L, and F into T1 of F star, right? So can you tell me what these two, what the domain and codomain of these vector spaces are?
The codomain is just F.
The codomain is just F. How about the domain?
No idea.
Yeah, well, it's not that different from what you just said for the codomain. Okay, GL and F, as we showed, is an open subset of F to the power of n times n. But F n times n is a vector space. If you have an open subset in a vector space, then of course its tangent space at any point will again be the same vector space. So this is nothing else but F n times n. You could just try to, I don't know, envision the Euclidean plane and then envision an open disk in it and try to ask yourself what the tangent space at any point would be of the disk. Okay, so how do we do this? Well, this now is, since we're dealing with vector spaces that we're kind of familiar with, we know how to deal with this. Okay, so first of all, this d that I should be tried to evaluate it on X. X is now any any matrix from F n times n. Let's try to evaluate this thing. Okay, we have the interpretation of tangent spaces and derivatives of maps in terms of curves. Okay, so this is precisely what we're gonna do. So the interpretation in terms of smooth curves says that we should, in order to get to the differential of a smooth map, we should differentiate the curve, sorry. So this is now nothing else but I plus Tx. I plus Tx is a smooth path in our domain, in GL and F. Okay, so in like a neighborhood of t equals to 0, we are going to end up in GL and F. So taking the determinant of map and taking the derivative at 0 with regards to t, we are going to get to our desired differential. Okay, so we have to somehow be sneaky now and determine the derivative of the determinant. Okay, so that's something that you may or may not have seen in your life, but I think this is something, one of the most important applications of like this analysis on manifold language and so on. Okay, so what we're gonna do is we're going to take this expression and we're going to start thinking about how to look at the determinant map in order to come to this derivative. Okay, so if you recall, the determinant is a multilinear map with respect to its columns. Okay, you if you multiply one of your columns by a, say, non-zero number, okay, you may take that number out in front of the determinant, okay, and just take the determinant of the original matrix. This means it's multilinear in its columns, right? So what we write here is now E1 plus Tx1, comma, dots, comma, En plus Txn. Okay, so now here we should write xi is the ith column of the matrix X. Okay, so by using what I just said, right, that is multilinear in its columns, what we get is, first of all, that E1, comma, dots, comma, En. Okay, and then for the second one, we just get like plus T. And now we're gonna get that x1, comma, E2, comma, dots, comma, En plus dots plus that E1 dots En minus 1 xn. Okay, so this is now by just taking all of the expressions that only have t, one t in them, right? So then we have about a bunch of crap here in between that we don't know how to say anything about, and then in the end, what we also have is t to the power of n times the determinant x1 xn. Okay, so this is now our expression. This det of I plus tx is nothing but this expression. So, but now what is this? Does anybody know what this is?
The the first component of the first column.
This is nothing else but x11. And this here is nothing else but xnn. Okay, so this means that so altogether this is 1 plus t times trace of x plus dots plus t to the power of n times the determinant of x, right? Okay, so this is really nice because now we see what's going to happen. Only the trace is going to survive, right? Trace of x survives and everything else falls away. Okay. So we've determined what the derivative of the determinant at point I is. Okay, so second of all, this should now be in the same in the same column or whatever. So what about d of that at point A? So how do we arrive to this? Any ideas?
We used the same thing previously.
Yeah, that's going to be a little bit more difficult. Okay. So there's this trick that we may use, and it's called the chain rule. Okay, so we have the following equality. So the determinant of, for example, let's take a to the power of -1x. This is equal to dit a to the power of -1 times dit x. Okay, now a is here. A is from, of course, S, L, N, C, or F, and x is from F n times n. Now, of course, this equality holds for any two matrices. You know, A doesn't have to be from special linear group, right? It's just the fact that the determinant is a homomorphism, right? That's all there is to it. So this here is nothing else but left multiplication by a to the power of -1 of x. So this is left multiplication now. All right. So what this means is that we have the equality determinant composed with L a to the power of -1 is equal to, so now this is 1 over that a, right? Because this thing here is nothing else but 1 over that a. And now times, this is not the composition sign, but times sign the determinant. Okay, so we have this equality. And what we do is we are going to take the derivative of this at a. Okay, so doing so, we're going to get d of that of LA to the power of -1 at a. So now this is only a number. Okay, what this means is by linearity of this d here, this 1 over that a is going to jump in front. So I'm going to get 1 over that a here. Okay, times d of that at point A. So on the right hand side, I am yielding the desired thing. On the left hand side, what am I going to get using the chain rule? What is this? Can anybody tell me?
So it's the derivative of determinant at LA at this map times the derivative of the map at
Okay,
point A.
but what is the point here of d of that? What's the point? What do I write in the index below?
Oh yeah, so yeah, so it's L of a -1 on A, so
Yes.
that's identity.
So that's identity, exactly. Because a to the power of -1 times a is identity matrix, right? So we get this and composed with d of L a to the power of -1 at point A. Okay. Well, but this map here, this is a restriction of a linear map. So linear map on f, well, f n times n to the linear map on GL NF. No, not to a linear map, but to a map, which is open. I mean, to a map. How do I say this? I restrict, first I have the LA -1. Okay, so the left multiplication. This is a linear map on f n times n. But then I have an open subset of this f n times n, and it's called GL and f, and I restrict this map that I have to this set, right? To GL and f. So the derivative of a restriction of a linear map is again the linear map itself, right? Just as in the case of any other vector space that you know of. Okay, so this means thus d of LA to the power of -1 at point A of x, this is nothing else but, so the original map, the LA to the power of -1, which means a to the power of -1 x, right? So, or equivalently, d LA to the power of -1 at point A is LA minus 1. Okay, but it has to be interpreted correctly. So this is more precise. The bottom equation is less precise. Okay, so finally, what we get is d of that A. So this is this thing here is equal to that A. So this is just this, right? And now I get times trace you're gonna have to, I'm sorry, you're gonna have to squeeze in an X here. Okay. And here we get A to the power of minus 1x. Okay, because now I'm using the result from the previous computation where we got the trace, right? So this is essentially just the trace. This is equal to trace. And as mentioned here, this is trace of this thing here, right? Okay, so I'm going to write this in a little bit more better way, so it's not all ugly and stuff. So, and this now is a really important equation. It deserves to be put in some brackets. Yeah, okay. So is this map surjective? This D of that A, is this surjective? Because what?
Can I just ask something?
Yes.
Didn't it say that A is from SLN? Wouldn't the determinant of A then just be 1?
Yes, but this is the this is a general formula that holds for A in GL and F. So you can write here A from GL and F and X from F n times n. Okay, we needed this formula. It obviously holds also for the case when A is from SL and F. But why is this map surjective?
Well, if we want to get some number from it,
Yes.
then we just plug X is A times X times the identity times the scalar, and that scalar must be the number we want to get divided by n.
Exactly. So I'm just gonna write because trace is surjective. Okay. So this immediately now implies that this S, L, and F is an embedded smooth manifold, so submanifold in GL and F. What is its dimension? Yeah, well, we just utilize the formula, right? Dim of GL and F minus dim of F. But this is the real dimension, not the complex dimension, of course, right? So now if F equals to R, what we get is that dim SLNR is equal to R, oops, sorry, this isn't okay, n squared minus 1, and if F is equal to C, we get dim SLNC is equal to, what's the dimension of GL and C?
Two n. Apparently not.
Squared. So 2n, and where do I put the square now?
In the brackets around it.
Yeah?
So it's 4n squared.
Are you sure? If
Yeah.
I have n to the power of 2 complex numbers, how many real numbers do I have?
Twice as many.
Twice as many. I don't have 4 times as many, right? So no brackets. Okay, and dimension of C is equal to 2, so this is 2 times n squared minus 1. Okay, I may also determine the tangent space at I of S, L, and F, for example. As we know now, this is kernel of D of determinant at I, and this is nothing else but the set of all traceless n times n matrices. By definition of the kernel of a map, of a linear map. Okay, so homework here is SLNF compact for any n you may think about this. Okay, we don't have much time left, but let's start solving this exercise, the following exercise, and we'll see how far we get. So, exercise. Prove that for P in natural numbers and Q from natural numbers union 0, the set O of PQ, which is equal to A in GL and R, such matrices for which the equality A T eta A equals to eta holds. So now, first of all, this n here, n is equal to P plus Q. And so let me write where eta is equal to diagonal matrix 1, comma, dots, comma, 1, and minus 1. And I have P ones and I have Q minus ones here. Is a smooth embedded submanifold in GLNR. So, do we have any physicists in the audience today?
A couple, yes.
A couple, yes. Do you recognize what this is? For example, for P equals to 1 and Q equal to 3.
Yeah, the metric, the Lorentz.
The Lorentz group, yeah, exactly. So let's have a remark here. O of 1, 3 is the Lorentz group. That's used very much in relativity. Okay, so one comment here should be made. We are proving that this is a smooth embedded submanifold in GLNR. Well, this so just as in the case for when we were considering the special linear group, we're proving the kind of the same thing, that this subset is a smooth embedded submanifold, and this now immediately implies that this that this group is not only a group, but it's a Lie group. Okay, so both special linear group and this O of P comma Q are Lie groups. I'm not going to write this down. So you are just restricting the multiplication in GLNR to a smooth embedded submanifold. Hence, your map is still smooth, right? As long as your multiplication ends up in the group again. Okay, so as long as this is indeed a subgroup, then this is a Lie group. Okay, so I see that we've run out of time. We're going to solve this exercise the next time, and then we're moving on to the tangent bundle and vector bundles, and so sections of vector bundles, vector fields on manifolds, and Lie derivatives, and so on. This is now beginning to get really juicy. Okay, do you have any questions?
When you say compact, do you mean in the topological sense?
Is there any other sense?
But just asking.
Yeah, it's the topological sense. I mean, of course, you have a notion of compactness in logic, but this is not a logic course. This is more of a topology in the smooth setting. So maybe differential topology / smooth category. Of course, compactness is purely a topological thing to consider in this course. You may also consider such stuff like components for path connectedness, okay? Not only compactness, but also if this topological spaces are connected or path connected or anything like that. So maybe we'll make some comments regarding that in the next exercise session. Okay, if there aren't any more questions, then I'll see you next week, next Friday.
Yeah.
Ciao.
Goodbye.
Yeah.
Bye.
Bye-bye.